Should I begin? It is 2:30. Or should we wait?
You may begin. Yeah, it's okay.
Dr. Ali? Should I begin? Okay.
Professor Sahai, just 1 minute only.
Okay.
Just 1 minute. We are making it YouTube live.
Okay. Okay.
Just
Please do. Please do.
switching it on only.
Please do.
Just it will take 1 to 2 minutes only.
It's okay.
Yes, so good afternoon, everyone, and welcome to the session 3 of ICSFA 2020. This is 19th annual meeting of Society for Special Functions and their application, and it is being hosted by the Department of Mathematics and Computer Science of Bhau Banarsi Das University. And in this session, we have 3 speakers, Professor Tom Koornwinder from University of Amsterdam, Netherlands, Professor Atul Dixit, and from Indian Institute of Technology, Gandhinagar.
You are not audible.
And Professor Dimitrii Karp from Holon Technological Institute, Israel. And I'm thankful to all the speakers for having accepted our invitation. And I'm also thankful to Professor Vivek Sai, who is a professor at Department of Mathematics and Astronomy, University of Lucknow, and he is going to chair this session. So, Professor Sai.
Thank you, Dr. Ahmad Ali. I extend a warm welcome to all the participants in this 3rd session of International Conference on Special Functions and Applications. Today is the 133rd birth anniversary of Srinivas Ramanujan, and this day in India is being celebrated as the National Mathematics Day. I have 3 speakers this afternoon in this session: Professor Tom Koornwinder, Professor Atul Dixit, and Professor Dimitrii Karp. So we begin with Professor Tom.
Can I start? Can I start?
Has published more than 110 research papers in reputed journals of mathematics and mathematical physics. His research interests are primarily in the area of special functions and orthogonal polynomials. He is the leading light behind the SIAM OPSF group. Today, he will be speaking on charting the Askey and QSC schemes. Professor Tom Koornwinder.
Well, thank you very much. I'm speaking from the Netherlands. It's 10 o'clock in the morning and the days are short here. I want to thank the organizers for the invitation to speak here. Well, 3 years ago, I was also at your conference in Bikaner, and I have good memories about that. So, today, first, the classical orthogonal polynomial scheme. Here are the Jacobi polynomials. Of argument 1 minus 2x. With this normalization, they're just terminating hypergeometric functions. And then they have weight function x to the alpha 1 minus x to the beta on the interval 0, 1. Compare them with Laguerre polynomials, confluent hypergeometric functions, weight function on 0, infinity, x to the alpha e to the minus x. Then with a slight rescaling of the Jacobi polynomials, we see immediately the confluence relation from Jacobi to Laguerre And we can also see this from the weight functions, rescaling the weight function for the Jacobi polynomials. We go to the weight function for the Laguerre polynomials. If we consider all classical orthogonal polynomials, Jacobi, Laguerre, and Hermite, and we all take them monic, so I will write them with small small size, small p, small l, small h. Here are the weight functions, and we can now see just by inspecting the weight functions limits from Jacobi to Hermite, and from Jacobi to Laguerre, and from Laguerre to Hermite. And in particular, the last one is not so well known, and it's most complicated to see it from the weight function. But now we want to consider this in a uniform way. So we want to choose. We want to do a rescaling for the Jacobi polynomials and choose parameters such that just by putting these parameters equal to 0, we can pass to Laguerre or Hermite. And here is the rescaling, the translation and dilation. And I express the dilation and translation parameters in terms of the alpha and beta of Jacobi polynomials, like this. And these rescaled Jacobi polynomials still satisfy three-term recurrence relation, and we can then compute the coefficients in the three-term recurrence relation, and we see that they are continuous in alpha inverse and beta inverse, bigger or equal than 0. And that's when we put alpha inverse equal to 0 or beta inverse equal to 0, we arrive at rescaled Laguerre. And if we put both equal to 0, we arrive at Hermite. So that's kind of baby example of uniform classical orthogonal polynomial scheme. And here you see the alpha inverse, beta inverse quadrat plane. Here we are the Jacobi, and at the two edges we are at Laguerre, and then here in the corner we are at Hermite. Now we want to do this for the whole Askey scheme. And this is an older paper of mine from 2009, where I consider the Askey scheme as a form manifold with corners. Here is the Askey scheme, and here is Dick Askey, who invented the Askey scheme, and unfortunately he passed away last year. I have made some special indications in this Askey scheme. On the left side, we have continuous families. Here at the right side, we have discrete families. And there is also the linear lattice, which is, there is the quadratic lattice. The quadratic lattice is in black, the linear lattice is in blue, and then the classical ones are in red. And all the arrows give limit transitions. Let's consider the Wilson polynomials, which are on top of the scheme. And I take them monic. So here they are, and they are expressed in terms of 4f3 hypergeometric functions. And we if you want to have orthogonal polynomials for positive orthogonality measure with these Wilson polynomials, then there are three possibilities. We can take two pairs of complex conjugate parameters, or one pair of complex conjugate parameters and two real parameters, or we can take the parameters all real. So for this, so here is everything depending on Wilson by limit transitions, but here is the case with the two pairs of complex conjugate parameters. Here only one pair of complex conjugate parameters, and here all real. Now I will also only consider for you this one, and then give a uniform parameterization of it. So we do rescaling, as I did earlier for the Jacobi polynomials, I choose new parameters A1, A2, A3, E4, and express the rho and the sigma and the A, B in terms of these new parameters. And here are the formulas for A and B and rho and sigma. And then the Monnick-Wilson polynomial still satisfies three-term recurrence relation, and can get very complicated formulas for capital Bn and capital Cn in terms of A2, A3, A4, which I will not give here, but you can see that Cn is bigger than 0, Bn is real, and both depend continuously on A1, A2, A3, E4 bigger or equal than 0. And we arrive then at the first Wilson subscheme. So that's on hyper octahedral upper plane, upper half plane. So there are four positive parameters, and they independently we can let them go to 0. So we can go to bordering hyperplanes and so on. So here you see where you arrive if you let one or more of the parameters tending to 0. And if you go in a slow way, we first go to continuous Hahn and then to Jacobi, then to Laguerre, or then to Hermite. But we can go in a very fast way and can go immediately to Hermite. Yeah, so in a sense, this is nice, but it's also very complicated. So we might wonder if there are neater ways to give a uniform parameterization. Now, let's go to the Q case, to the Askey-Wilson polynomials. So I recall the Q-Poghammer symbol given by this, and if you have a product of Q-Poghammer symbols, we write it like this. And then we have the Askey-Wilson polynomial, which I will consider monic in Z plus Z inverse, because Z and Z inverse, they enter in the 453 q-Hypergeometric representation for these Askey-Wilson polynomials. I take it monic, but the coefficients, because of the monicity, I take here. So so you can see that they are polynomials in Z plus Z inverse. And of course, if Z and Z, if Z is on the unit circle in the complex plane, then Z plus Z inverse is real. Okay, so this is the 453, and by the definition of 453, this is terminating series like this, where the q-Hypergeometric symbols enter. And I will split it a little more, these vectors here. And yeah, we have here the vectors which depend on z. Here the vectors which depends on n, and here vectors which only depend on k. Now I'll write it once more. Now I will define expressions xk, hk, and gk, which are Laurent polynomials in the q to the k, with coefficients depending on a, b, c, and d, like this. And if I enter these expressions here, then this takes the following form. Yes, so this seems to be a little strange, but it's in fact it's very useful. So this modic Askey-Wilson polynomial, which let's say call it unx, has an expansion as a sum cnk of vkx, k running from 0 to n, where vkx is a kind of Newton polynomial, product of x minus x0, x minus x1 up to x minus x k minus k minus 1, where the xk is given by this. And yeah, the c and k is this product, and we can now see, yeah, still in the Askey-Wilson polynomial case, but also more general, that the UNs are eigenfunctions of a certain operator capital L with eigenvalues Hn, where the operator L is defined by letting it act on these v sub k's, on this v sub n, and then it should be given L of Vn by Hn Vn plus Gn Vn minus 1. And also the operator capital X of multiplication by X has a nice form. If we let it act on Vn, then it's Xn Vn plus 1. Now, and I assume that the Hk and the xk are Laurent polynomials in q to the k, and that gk is Laurent polynomial of degree 2 in q to the k. And I assume that the sum of the di's is 0, and that the d3 and the d4 have an expression in terms of the a1, b1, a2, b2. Well, these constraints, this and this, can be verified to hold in the Askey-Wilson case. But we now look at any UN of this form, and now the nice idea of Louis Verder-Star in a preprint of earlier this year is that we can take the AI, BI, and DI parameters with the constraints given as parameterizing the QSC scheme. So here is Verder-Star Here is the title of his preprint. Well, the QSC scheme, here is the chart made by Koek and Zwartau. And yeah, so many arrows, many families. So I write again what I already had. The UNs, the Newton polynomials Vk, the CNKs, the xk, hk, gk, and the constraints. Now I observe that there are also some invariances. So we can translate the x variable by sigma. Then everything remains invariant if he also translates the xk by sigma. And we may translate its hk by tau, but because hk here only occurs as hn minus hg, it makes no difference. And then we have a dilation invariant. We may dilate the argument of un by rho, and then still keep it monic. Then also adapt vk, and then we adapt xk and gk, and then everything remains invariant. And we see also that things are homogeneous of degree 0 in hk, gk. So we can multiply hk and gk by mu and nothing changes. So we see that we have 3 plus 3 plus, excuse me, no, I have to go back. Yeah, we have 3 plus 5 is 11 parameters and 3 constraints and 4 invariances. So we are left with 11 minus 3 minus 4 is 4 essential parameters. Can also observe that we have Q inverse exchange just by flipping A1 and A2, B1 and B2, D1 and D2, D3 and D4. Now, I write again this xk, gk, and dk. It's the expansion as Laurent polynomials in Q to the k, and I just represent it by this symbol. And I'm particularly interested when these coefficients are 0 or non-zero. Well, black here denotes any parameter value, and open circle 0 parameter value. This white circle means 0. So SE Wilson corresponds to this symbol. Oh, I see time is running very fast. So, okay, there are a few rules for this symbol. If the B1 or E1 is 0, then the D3 is also 0. If the B2 or A2 is 0, then the D4 is 0. I keep the B0 and A0 always black. In the second row, no 0 between 2 black ones. In the second and third row, at least 2 black ones. Flipping a black one into a 0 one causes an arrow between the symbols. And then reflection with respect to the central column means Q and Q inverse interchanged. A reflection with respect to middle row between duality between X and lambda n. Now, and here is my scheme. So this should be the combination of my lecture. So I already showed you this QSC scheme according to Koeker and Swarto. And here is my scheme following Verde star. And you see in with each arrow there is further flipping from black into white. Well, and in the next, I have replaced the symbols by the names, and for each symbol there may be several names, because we are not classifying here orthogonal polynomials for positive orthogonality measures, but here we are classifying q-Hypergeometric families together with the monomial type families in which they are expanded. Both the continuous and discrete family may stand on the same place. So in the top, Askey, Wilson, and Q Raka. Yeah, you see that there also degenerate cases occur, which certainly are no longer orthogonal polynomials. Well, it's yeah, let's see. Yeah, I have a few observations about it, which I just flash for you without commenting, because my time is over, and I think I should stop here. Yeah. So let me start thanking you, which I already did. And here a picture of the full moon, which I saw in my 3 years ago in my last night in New Delhi. And then 1 or 2 days later, there was the worst fog ever in New Delhi. But I was lucky to see this full moon. Thank you.
Thank you, Professor Koornwinder, for this enlightening lecture. I can see Professor Atul Dixit. Yes.
Hi.
So he's our second speaker in this session. Professor Atul Dixit is at IIT Gandhinagar, Indian Institute of Technology. He did his PhD from University of Illinois at Urbana-Champaign, and his research interests are number theory, special functions, theory of partitions, and Q-series. He has published more than 45 research papers, and he says that he likes to work in areas inspired by Ramanujan. Today, he speaks on generalizations of the third order mock theta functions omega q and nu q. Professor Dixit.
Thank you very much, Professor Sahai. I would like to thank the organizers, in particular, Dr. Ahmad Ali, for organizing this meeting and for inviting me to give a talk in here. It's really a pleasure. I would like to share the screen first. Can I do that? Huh?
Yeah, go ahead.
Can you see this?
Yes, now we can see it.
Okay. So I'll be talking about some generalizations of the third order mock theta functions omega of q and nu of q. This is joint work with Bruce Berendt and my PhD student Rajat Gupta. So I will begin by saying that one of the most important discoveries of Ramanujan are mock theta functions. And we are all seeing the applications of mock theta functions in areas where we did not hope there would be applications, for example, in string theory, black hole, and whatnot. So they are finding their ways in all areas of mathematics and mathematical sciences in general. Today, what I'm going to do is to have the perspective from, a combinatorial perspective towards mock theta function. So let me first say that a mock theta function may admit a simple and interesting combinatorial interpretation. For example, I consider one of the fifth order mock theta functions of Ramanujan, summation n equal to 1 to infinity, q to the n upon q to the n sub n. Now, what is this notation? I'm pretty sure everybody knows, but let me do this for the sake of completeness. So a sub 0 is 1, a sub n is the q shifted factorial, the base is q, and this is nothing but 1 minus aq, so on up to 1 minus aq to the n minus 1. And if you assume mod q less than 1, then we can let n tend to infinity. This is a conversion infinite product, and we get basically 1 minus a, 1 minus aq, 1 minus aq square, and so on. So what is this interpreting? You see, the first, if I denote by n the smallest part in a partition of some integer, then I have q to the n upon 1 minus q to the n. Of course, I need that q to the n in the top, because what is this telling us? That you have a smallest part n, and any partition which does not have a smallest part ought to be empty. So one must have q to the n upon 1 minus q to the n. If it were just 1 upon 1 minus q to the n, then that means that, okay, the smallest part may or may not appear, but then the partition has to be empty. And from the point of view of analysis, the series would be divergent if there were no q to the n here. So this is essentially from both combinatorial as well as analytical perspective. So here we have n denoting the smallest part, but then the parts which are bigger than the smallest parts, how many can we have? N plus 1, n plus 2, so on up to, what is the last term here? It's n plus n minus 1 in the exponent. So 2n minus 1. But then we cannot have 2n. So this is nothing but generating function for partitions in which no part in that partition is as large as twice the smallest part, because there is no part which is equal to 2n or greater than 2n. So that's the combinatorial interpretation. Now, about 5 years back, George Andrews, Ajay, and myself, we worked on one project where we studied some restricted partitions, especially those in which each odd part is less than twice the smallest part. So let me say by means of an example, I consider the 11 partitions of 6. These are listed here. Which are the partitions that cannot come in here? You see, the odd part, every odd part has to be less than twice the smallest part. So I will have to drop this 5 plus 1, because the smallest part is 1, twice the smallest part is 2. No odd part should be greater than twice the smallest part. So I cannot have 5. Similarly, I cannot have this one, 3 plus 2 plus 1, because again, twice the smallest part is 2, and I'm having 3, which is an odd part. And I cannot have 3 plus 1 plus 1 plus 1, because again, 3 is greater than 2 times 1. So these 3 partitions have to be omitted. What about this 4 plus 2? Of course, there are no odd parts here. The smallest part is 2, twice the smallest part is 4. There is no odd part, so it is vacuously true. So I have p sub omega of n equal to 8, because these 3 are removed out of the 11. If I look at the generating function for this p sub omega of n, what is it? Again, I have n denoting the smallest part, so I must have this q to the n upon 1 minus q to the n. Starting from part which is greater than smallest part, it may or may not appear, right? So that's why I don't have any q to the n plus 1 in the top. I just have 1 upon 1 minus q to the n plus 1, or 1 upon 1 minus q to the n plus 2, and so on, up to 1 upon 1 minus q to the 2n. Okay, so starting from n and going up to 2n, is there any restriction on the parity? That, okay, only even parts can come or only odd parts can come? No restriction. The part can be even or odd. But once you reach twice the smallest part, note that here the base changes to q square, which is telling us that there cannot be any odd part. After 2n, there can be 2n plus 2 or 2n plus 4 or 2n plus 6 or 2n plus 8, whatever. But there cannot be 2n plus 1, 2n plus 3, 2n plus 5, and so on. So that is what is being expressed here. Every odd part has to be less than twice the smallest part. So this is the generating function for p sub omega of n. And now what is this generating function equal to? I mean, one can define innumerable restricted partitions where one has conditions of this kind. But are there generating functions? Interesting. Are they related to some already studied objects which are of quite importance? That is the important thing. So the answer is yes. And you may have noticed that I have put here omega. So it has to do something with the omega of q, which is the third order Mach theta function of Ramanujan, which Watson also rediscovered. So this is given by summation q to the 2n square plus 2n upon q square sub n plus 1 square. And what it turns out to be is that it is nothing but, I mean, the q times omega of q, nothing but the generating function of p sub omega of n. So these restricted partitions with these restrictions on the odd parts, they have as their generating function essentially the Mach theta function omega of q. So let me go to another function, which is p sub nu of n. Again, nu is there because of some reason. So if I look at the same restrictions that I had before, that each odd part has to be less than twice the smallest part. But in addition, I'm requesting that the parts be distinct and non-negative. So for example, if I take again the partitions of 6, but now see, I'm allowing my parts to be non-negative. That means my part can be 0. So there won't be 11 partitions. There will be more than 11. I mean, where 0 also occurs as a part. So out of those, the ones which qualify in here are these 4 only. First of all, these are partitions into distinct parts, and all odd parts are less than twice the smallest part. So you see, if I go back here, all others drop out because they aren't partitions into distinct parts. There are repetitions here. Okay, so the only ones are 6 and 4 plus 2, which satisfy this requirement also, and plus the requirement that the parts are distinct. But because I'm allowing the parts to be non-negative, I can also have 6 plus 0 and 4 plus 2 plus 0. Now, what is the generating function here? Note that it will be this. Again, my n denotes the smallest part. And because it is a partition into distinct parts, so there cannot be divided by 1 minus q to the n. Because when you expand q to the n upon 1 minus q to the n, what is it giving? Q to the n plus q to the 2n plus q to the 3n plus dot dot dot. That means the smallest part may or may not repeat. But I do not want the smallest part to repeat. So I cannot have anything in the below as 1 minus q to the n. So this is representing the smallest part. This is again, if you omit the sign for a time being, you have parts from n plus 1 up to 2n where you can have even or odd, no restriction, but they must be distinct. So I'm including this minus sign. And after 2 times the smallest part, you cannot have any odd part. So the base has changed to q square, but because of distinctness, again I have a minus sign. And why do we have non-negative? Because I'm starting at 0, not at 1. Okay, so this is our generating function for p sub nu of n. But what is this equal to? Very nicely, this is nothing but another third order Mach theta function of Ramanujan at minus q, not at q, but at minus q. So this is the nu of q function of Ramanujan and Watson. Now let me look at 2 more results, and then I'll make all those related and then move towards the generalizations. So if I look at Euler's pentagonal number theorem, what is it equal to? This is a series product identity, and it gives a series representation, a bilateral series representation for q sub infinity. If I had minus q sub infinity, that was a generating function for partitions into distinct parts. But because I'm not having minus sign, what happens is I have 1 minus q, 1 minus q square, 1 minus q cube. So you see, it depends on how many powers of q I multiply so that I get a plus sign or a minus sign, right? If I multiply odd number of powers of q, then I will get a minus sign. If I multiply even number of powers of q, I will get a plus sign. So I group the partitions into distinct parts into 2 cases. One that have even number of distinct parts, and the other which have odd number of distinct parts. And then what is this Euler's pentagonal number theorem saying? That if dE of n enumerates the number of partitions of n into even number of distinct parts, and similarly for dO of n, then they are almost always equal. When are they not equal? Exactly when n is a generalized pentagonal number. And what is the difference? It's either plus or minus 1. So they are almost always equal, but they differ by plus or minus 1 depending upon whether we hit a pentagonal number or a generalized pentagonal number. And this is a version due to Legendre. Okay, so in the same vein, how can we get some analogs of Euler's pentagonal number theorem? Meaning, what I'm going to do is, if you see the result that we had for omega of q as the generating function for p sub omega of n, I did not have a minus sign here. I had a plus sign, but now I'm making a minus sign here. So what happens is exactly what you had on the previous slide, a similar thing. Like when it was minus sign, it was partitions into distinct parts. But when I have q sub infinity, I need to look at how many powers of q I'm multiplying before I get a plus sign or a minus sign. So when I make this minus signs here, I'm actually grouping or bifurcating the partitions in which each odd part is less than twice the smallest part into two groups. The ones which have odd number of parts, the other which have even number of parts. And again, you have a similar result as Euler's pentagonal number theorem. That is, these two are almost always the same, except when you hit a number of this form, 6j square plus 4j plus 1 or 6j square plus 8j plus 4, 8j plus 3, sorry. So this is coming from here, as you can see, this or the addition of these two. And one more thing, where in the top you had a minus sign when you were having nu of minus q, but now you are having plus signs. So again, a similar thing is happening. And accordingly, you have again the addition of this distinct non-negative parts. And then you can have an analog of Euler's pentagonal number theorem. Okay, having discussed these four identities, I would now like to bind them together. How do I do this? Well, for that, I require generalizations of mock theta functions due to George Andrews. He gave these generalizations for third order, I think only third order mock theta functions in 1966. One of which was this omega of z comma q. And now you can clearly see if z is 1, it gives me omega of q that was there previously. So this is a one parameter on one variable generalization of the mock theta function. Andrews and Yee recently wrote a paper where they studied a new generalization of nu of q, which is here. Again, if you put z equal to 1, you get back nu of q. This generalization, why is it denoted as nu sub 1 of z comma q and not nu of z comma q? Because Andrews earlier had given another definition for nu of z comma q. And the one that they require is this different generalization. So in this paper, very beautifully, they put all these four theorems into just one, into just two identities. And how did they do that? Just observe all four theorems. Sorry for going that back, but here you see, I can put this in here, right? This becomes q sub n plus 1 here. And that is with a plus sign. Then when I go here, you see the same thing, but with a minus sign. Now, what they had in mind was, okay, what if there is a parameter z in here? And then when you put z equal to minus 1, then you get this result. When you put z is equal to plus 1, you get that result. And similarly, if you look here with the generating function for p sub nu of n, I had a minus sign here. And now look at all other things. They remain the same exactly, except that here I have the plus signs. So again, they had this thought. What if we put a parameter there or a variable z? And when z is plus 1 here, we get this result. When z is minus 1 here, there is another result, the one that I discussed before. But it's very rare that one is allowed to put a variable and yet retain an identity that is very, very beautiful. And that's what exactly happened in their case. They got this very beautiful generalizations of my results with them. This paper appeared just last year. So again, all four theorems come by putting either z is equal to plus 1 in both here and here, and z is equal to minus 1 in both here. And you get you can get to those four results. Their proof relies on using these two finite summations, and which are also new. They were not able to find this in the literature. Now the thing is, their proof requires knowing these two identities in advance. I mean, maybe they were found experimentally first and then they proved it. But how about going from one side and getting the other? Or going from this side and going to this left-hand side? Is that possible? So yes, so that's what we started as our initial plan for our project, to try to get more natural proofs of their beautiful identities. But then our next goal was to generalize the Andrews-Yee identities. Why do we want to generalize? Is it just for its own sake, or does it have some important implications? The answer is the latter. There are some important implications, and before giving those identities, I would like to explain those implications. So there are already 3 variable generalizations which people have considered. Very recently, there was a paper due to Li and Yang where they have additional variable y. So again, if you put y equal to 1, you'll get back Andrews's generalization of the mock theta function. Here, if you put y equal to 1, you get Andrews and Yee's generalization of the mock theta function. But they were not the first set of people who actually got these 3 variable mock theta functions, 3 variable generalizations of mock theta functions. Yunsa Che had already done this back in 2011, and one can get back and forth between Yunsa Che's definition and Li and Yang's definition of these. Okay, I won't go into the proofs of these, but one can go back and forth. This one is slightly preferable because you see symmetry in Y and Z, which is not seen in the Yunsa Che's definitions, although one can get by simple change of variable. Why is generalization of Andrews-Yee identities important to seek? Let us consider this 3 variable generalization of mock theta function. We can write this in terms of this function g of a comma b comma q. This function appears in Ramanujan's works. In Lost Notebook, there are many results devoted to this function. In fact, there is one monograph of George Andrews called Partitions Yesterday and Today, where he very beautifully, completely in a combinatorial fashion, he gives identities related to this particular function. But this function is also important from analytical perspective because it is linked to what is called as the universal mock theta function of odd order. So if you remember, there is a work of Gordon and McIntosh where they say that all of the mock theta functions of odd order, say 3rd, 5th, 7th, they are special cases of G sub 3. And all mock theta functions of even order are special cases of G sub 2, another thing. So this G sub 3, universal mock theta function of odd order, is actually a special case of, is related to this, which is a special case of G of a comma b comma q, which is in fact, can be written in this form, I mean vice versa. So if you get Andrews-Yee type identity for this, then that will allow you perhaps to get Andrews-Yee type identity for this G sub 3. And why is that important? Because up to now, I have shown you only for 3rd order mock theta functions. But if this is giving me mock theta functions of any odd order, that means I can do the same for 5th order mock theta functions, for 7th order mock theta functions. So that is the goal. However, this goal is very far-reaching. We haven't been able to reach this goal, but we have made some progress in a different direction. And before I come to that, let me say, this is something that I just explained in words. But here I would like to say that Li and Yang, at the end of their paper, they say that finding generalizations of 3 and 4. What are 3 and 4? The Andrews-Yee identities. For these 3 variable generalizations of mock theta functions remain mysterious. So nobody has been able to get really those generalizations up to now. But fortunately, we have solved this mystery to some extent. So till what extent, let me explain. See, if you want to generalize these Andrews-Yee identities by putting one more variable, let's say y or alpha, whatever, we are putting it by means of alpha. We are not in a very nice situation similar to how Andrews and Yee were. So remember the first 4 results in my talk. There were plus plus, minus minus, minus minus, and plus plus. And they just very rightly put the parameter z there. Okay. Now, if you want to extend their identities by putting one more variable, where do we put that variable alpha? I mean, in Q series, you all know, right? Whenever we have a Q analog of something, that Q can appear, Q analog of certain hypergeometric identity or whatever, that Q can appear in innumerably many places. And one has to really look at what is the natural choice. Sometimes it is trial and error. Sometimes one has to really see how important are the generalizations that we have obtained. And that was how, that was what our benchmark was. Okay, are those identities important? Do they give some important results as special cases apart from merely generalizing their identities? So with that, I would like to say that people have generalized Andrews identities in different directions, like Wang and Guo. So, oh, sorry, Wang and Ma. Sorry, Wang and Ma have generalized it where the Q here was generalized to Y, but they did not put any other place Y. Or here, again, there was a Q to the N. They replaced it by Y to the N or Y to the N minus 1. But what happens here is that because of that Y taking place of that Q, remember we always used to say with the Q to the N, combinatorially, that N was denoting the smallest part. Now, once you have this Y to the N, that sort of combinatorial interpretation is compromised. So even though they have Q series identities from here, there is no combinatorial explanation to those. So what we do is we work with these two generalizations of three variable of the Andrews-Yi identities or Andrews and Yi mock theta functions. So first of all, this is a work which we have recently submitted for publication, and in there now, why you may say why we choose nu and omega 1 and not omega naught that Li and Yang had on something else. So this is again, if you put alpha equal to 1, you get back to the mock theta functions that, or the generalizations of mock theta functions that Andrews and Yi employed in their identities. And if you put further z equal to 1, then you get back to Ramanujan's mock theta functions. But why these two only? Why not any other place, any other series where alpha appears at a different place? So there should be some logical reasoning why these are chosen over the others. And here is something. First of all, as I said, alpha equal to 1 gives their mock theta function, Andrews' mock theta functions. And if you put z equal to 1 again, you get back to Ramanujan's. So in all of these results, starting from my work with Andrews and Yi, and then Andrews and Yi's work itself, there was this functional relation between the two mock theta functions. There is a relation between these two mock theta functions which played a crucial role. So if you put z equal to 1, then you get back the relation between nu and omega that Ramanujan gave. But here is more general relation due to George Andrews. So in our natural proofs of their identities, we employed this relation. Even in my work with Andrews and Yi, we employed the z equal to 1 special case of it. And so it is natural that, okay, if you are further generalizing those identities, then whatever generalizations of the mock theta functions that you are taking, those should have some kind of relation between the new generalization and omega generalization. And here is what we have. These two mock theta functions which we are considering, they are linked by this functional relation. And you very nicely see that when alpha equal to 1, this summation q to the n square plus n becomes this q product, as can be seen by Jacobi triple product identity. And this, when alpha is 1, you have minus zq q square and zq q square. So that becomes z square q raised to 4 sub infinity. Okay. So this is what gives us this zq by alpha becomes zq, and you very nicely see this one. So this is the binding thread that, okay, there is functional relation all throughout the generalizations. So there is some kind of trade-off. I know I have, do I have 3-4 minutes? Can I take? Okay. So what is the trade-off? The trade-off is that in our first, the generalization of their first identity, we got an expression for omega 1, which is what was desired. that there is alpha, z, and q, all three independent parameters. But for the second one, their second identity, our generalization involves again alpha, z, and q. But if you see the first component here and the second component here, they are related. I mean, you take just minus of this first component and that is your second component. So it's not really three independent parameters, mu of alpha, z, q. No, we could not get those. But on the other hand, this one, the identity which has this all three independent parameters, that is somewhat more complicated. The identity which has dependent parameters or dependent components is somewhat simpler. Okay, so that is the trade-off. What do you want? Do you want independent parameters or do you want a simplified identity? Those sort of, that's the trade-off that we had to look for. We could not get so far the identities where the generalization of their second identity where we would have three independent parameters and the generalization of the first identity where we had dependent parameters. So here is our generalization of their second identity. You see, when I put alpha equal to 1, here is minus zq q sub n. Here you have minus zq q sub 2n. So I start with minus zq to the n plus 1 sub n after cancelling all these. And that is what was there on the left-hand side of their identity. But the right-hand side is, how do we get their right-hand side when alpha is 1? So that requires two results. First of all, Andrew's 4-parameter Q-series identity is all throughout these analysis is a very powerful identity, very useful. So by doing that, this left-hand side we have transformed into this part. But I won't go over the proofs of that. I will instead say how we get their identity as a special case. And that requires this reciprocity relation between the new mock theta function, which follows from Ramanujan's reciprocity theorem very easily. So this is a very well-known theorem. You do some substitutions and you get to this. Okay, so how do we get their second identity as special case of ours? So as I said, the left-hand side turns out to be this. And when alpha is 1, you see there was alpha square here, minus alpha square here. So all that becomes 1, 1. Here is where we apply the reciprocity relation. 1 by z minus 1 by z minus q. If you see on the previous slide, it's 1 by alpha minus z by alpha. So alpha becomes, z becomes 1 and alpha becomes z later on. We have to substitute that. So using that, this can be written as a q product minus this. So that's what we do here. And now for this sum here, one can use the q analog of Gauss's second theorem, which again gives a q product, and that q product exactly cancels with here, giving us this result, which is what they had. I mean, note that there is a minus z here, but there is a minus 1 by z here. So that gives us just nu 1 of z comma minus q, which was their identity. Now, there are numerous special cases of those which I won't go into, but let me end it by saying that we have the generalization of their first identity. As I said, it involves all three general variables, alpha, z, q. But it's somewhat complicated. But in this generality, you cannot expect anything better. You cannot expect something that they had. Like this series equal to this something where you have a mock theta function. You have to have this extra part, which becomes 0 when alpha is 1. And I won't go into the derivation of how we get their identity as a special case, but I would like to just say, and this is my last slide. Yeah, this is my last slide. If you look at this omega mock theta function, it satisfies this beautiful relation. You replace alpha by 1 by alpha and z by minus z by alpha. So this becomes here and this becomes this. So it just becomes the same thing. So you get back this omega 1. And not only is that true, the left-hand side here also is doing the same thing. And so this complicated expression that we saw, I mean, at first glance, this looks quite complicated, but this is satisfying some really nice symmetry. This f alpha zq is f1 by alpha minus z by alpha q. So far, we haven't been able to utilize this to our advantage, but we plan to do so in some future work. Thank you very much.
Thank you, Dr. Dixit, for this interesting lecture.
Thank you.
Do we have Professor Karp on with us?
We do have. He already has joined.
Okay.
He has joined. He is in the room.
Okay. Okay. So I can't see him. Okay.
I am supposed to be next speaker. Hello.
Yes. 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 Professor Karp. Right. 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 So the next speaker is Professor Dimitrii Karp from Holon Institute of Technology, Israel. His primary interest is in the field of special functions, and he has published more than 40 research papers. And we look forward to his talk. He will be delivering the talk on reduction formulas for quadratic forms composed of hypergeometric and q-Hypergeometric functions. Professor Karp.
Thank you. Thank you for presentation. Okay, I'll try to share my screen now.
Yes.
Okay, is it visible?
Yes, yes.
Okay, so, I think in this audience, there is no need to define the hypergeometric function.
Right.
But my first slide is the definition. We will usually use this vector notation. So A, well, not in some cases we will use. So A is the vector, generally complex. B is a vector, and then we have this standard definition of generalized hypergeometric function, which probably everybody in the audience know very well. Okay, we will deal with mostly with the case when p equal q plus 1, but sometimes also with the p does not exceed q case. Okay, given this definition, let me go to the history a little bit. Sorry, this was the wrong direction. So if we take very standard and classical and easily derived Euler's formula here, then we can write it in a little bit weird way, I would say. We could write it like the next formula here. So how do you get one from another? If you simply apply to this expression, this identity, and do the same with this expression, again, apply this Euler's identity, you simply get the same thing here and here, so you obviously get 0. But this form, which is quite weird, hints at possible generalization. And indeed, there is a kind of formula of a similar flavor attributed to Gauss. I don't have a direct reference, but in some articles I've seen it attributed to Gauss. But here the difference is that we have 1 on the right hand side, not 0, and we have some coefficient here. And then the parameters are also kind of similarly reflected, not exactly the same, of course, but a kind of similar reflected parameters. Then there was a gap. This slide I call prehistory. So then there was a gap. And next, why does it move? Let me see. Next step was, as far as I know at least, was made by Darling in a nice paper published by Proceedings of London Mathematical Societies in 1932, where he proved kind of similar formulas, but for higher order hypergeometric functions. In particular, he had a formula for F32. In this formula, F equals F32. And we also have a sum of 3 products equal to 0. And his proof is based on the properties of generalized hypergeometric differential equation. And actually, he derives a certain formula for kind of Wronskian or mixed Wronskian, and then this identity follows from this Wronskian identity. He also made a generalization to F4 free. So this is a formula for F4 free from Darling's paper. Again, we have products, but now we have 4 products. We have 4 products with certain coefficients depending on parameters, and the sum of all 4 equals to 0. He also hinted at how to derive a generalization to Fp plus 1p. Then immediately after that, in the same journal, there was a follow-up paper by Bailey. The funny thing is that the title of the paper by Bailey is the same except for 1 letter as the paper by Darling. Darling had on certain relations between hypergeometric series of higher orders, and Bailey wrote certain relations between hypergeometric series of higher order. So except for S at the end of this word, the title of the paper is precisely the same. And Bailey showed how identities that I have just shown, identities due to Darling, can be derived without any appeal to differential equation. Instead, he used contour integration and also showed how to extend it to FPQ, to general FPQ. He also gave a Q analog in terms of basic hypergeometric functions, which I will define a little bit below, but you have already seen a big bit of Q analysis in Atul's talk. So basic hypergeometric function also satisfies kind of relation of the same sort. This was derived by Bailey. Then more modern developments are contained in many papers. First, I would like to mention the work of Nesterenko, which is devoted to Hermite-Padé approximation of generalized hypergeometric functions, so systems of hypergeometric functions, and published by Zbornik Mathematics in 1995. He used very non-standard complicated notation, so probably his result, as a result for duality relation or this kind of quadratic form identity, was largely unnoticed, but he actually had an identity -1. Gorelov was aware of this result and found the generalization in 2010 using again some fine properties of the generalized hypergeometric differential equation. Independently, because they do not refer to Nesterenko and Gorelov, Boykers and Johet discovered another relation of the same spirit, which I will now show you. And they used completely different algebraic proof using this theory of D modules and also algebraic properties of differential equations. Well, I honestly cannot understand their proof, so I can just say the names of the methods. The identity that they have got is the following. So we have the solutions. This is the set of solutions of the hypergeometric differential equation. And this is a kind of solution of something they call dual equation. So if we denote them by Fi and Gi, then the following identity holds, where theta is this standard differential operator, z times derivative with respect to z. So we have derivative, well, this generalized derivative, or sometimes they call it, I forgot. Anyway, to the power k of the function f then derivative of the order L of the function g. Then we take again sum of products with certain coefficients, and we get something simple. This MKL is a kind of simple function. They give explicit formula for k plus L not exceeding r minus 2, or k plus L equal to r minus 2. And then they give also the recipe for other cases. But there is certain restriction in their result that k and L run only between 0 and r minus 1. You cannot take them bigger. They also presented a Q analog. Which I will not show here, but also using the Q difference equation satisfied by the basic hypergeometric function, they derived the Q analog. Okay, so, but the flavor of all these formulas is always it's a sum of products of certain hypergeometric functions with certain structure, special parameter structure, maybe also with powers of them. Okay, well, there were several other papers in the same period after 2010. Ebisu worked on three-term relations for hypergeometric functions, which are classical relations, but he managed to derive explicit formulas for general three-term relations. General, I mean with arbitrary integer shifts in parameters. And as a byproduct, he found the relation for F21 function. So in Ebisu work, sorry, what happened here? Ebisu work is about F21 function only. Why doesn't it work? F21. Our paper with Kalmykov, we were unaware of Ebisu's work, and we derived an identity for F11, which later we realized could be derived as the limit case of Ebisu's identity. Then there was a very important paper of Alexei Kuznetsov with Feng and Yang, and they found an identity for general FPQ now, and also a Q analog for basic hypergeometric function. I will not show you the formula because the formula that we derived is a direct generalization of the formula from that paper, and this it will be given as a particular case. Then there was the work of Yamaguchi, who generalized Ebisu, and his purpose was to find three-term relations for basic hypergeometric functions of the type of phi, if you want, phi to 1. Also, he found explicit formulas for the coefficients of three-term relations for phi to 1. As a byproduct, he had a certain identity for the kind of also sum of two products of phi to 1 functions with certain parameter structure. Okay, so now I come to our paper. This is our general, theorem. Well, I'll give you the reference, but this is a paper by Alexei Kuznetsov and myself, published by Proceedings. We use this vector notation here. If we take two integer vectors, positive or negative, we can take both. We take two complex vectors, A and B. And then if you see a sum of a vector with a number, with a scalar, just element-wise sum, and the expression like this for Polynomial is a product, okay? If A is a vector and N is a vector of the same size, then this is a product. Then we need also the maximum of n of these integers, minimum of these integers m, sums, and then we define a special number p, which is maximum of -1 and the m minus n minus r minus +1. So r is the index of the hypergeometric function. Then the following general identity is true. So you can see it is in the appearance is a kind of similar to all previously shown identities. So this is a product of Polynomials, but then we have some numbers beta j here, and well, up to now we don't have explicit expressions for these numbers, although for the case r equal 1 they can be derived from results of Yamaguchi. Well, I believe these numbers can be expressed as hypergeometric polynomials, but it is still open, the explicit expression. The important thing are these two numbers, minus n max, p minus m min. For relatively small shifts, these are small numbers, so the right-hand side becomes something extremely simple. So the basic idea is that this infinite series on the left-hand side becomes some Laurent polynomial times this power of 1 minus t of small degree, Okay. Sorry, I also forgot to say that this a with the square brackets I means vector a with eth elements omitted. So this is, we take a I and remove it from this vector. Okay, I hope this identity, at least its shape is clear. And we also have the restriction that a elements, components of a should be distinct modular integers. ai minus aj should not be an integer number. I give you some examples of the right-hand side for r equal 3. So for r equal 3, you can see that the right-hand side, the left-hand side is explicitly given here. So what will be this betas, the right-hand side? Well, if n is 1, 1, 2, m is 1, 1, 2, just an example, 1, 2, 2 is an example, we get such a simple expression. So this Laurent polynomial just has a one term with the negative square 2. Z negative z square, or 1 divided by z square, reciprocal of z square. For these parameters, we get again just one term, negative cubic term in the Laurent series on the right-hand side. So in all these examples, you see only one term. This is just to give you an idea that for relatively small values of the shifts, n and m, we get relatively simple expressions on the right-hand side. Anyway, these expressions can be easily found by using some computer algebra like Wolfram Mathematica or other software. Our second theorem is the confluent case. That means instead of r minus 1, we now have s here, where s does not exceed r minus 1. We get a kind of similar relation, but now this coefficient that we had here before, 1 minus z to the power something, does not appear. And we simply have this Laurent polynomial. Also, the degrees get modified a little bit. This number p has now new definition, and the degrees get a little bit modified. But basically, you get a similar relation for the case when s does not exceed r minus 1. Okay. Here are a couple of particular cases of the confluent relation. Well, I don't think the identity for Bessel function is new, but this is what we get if we take f01. In other words, if we take Bessel functions, the classical Bessel functions, then you get this. And here it's very easy to complete the numbers beta g because the product is very well known, so it's no problem to complete these numbers. If here is an example for f11, just an example. Then we get this kind of linear term on the right hand side. Okay, I hope this is clear. We have many more examples that are easy to compute, as many as you like. Okay, what about Q analogs? Yes, we also have Q analogs. Here are some Q definitions which you already know from the previous talk. Let me just quickly remind for people who just joined. This is the standard Q-Polynomial symbol, the product of this type. We also will need Polynomial with negative index, which is defined in this way. Both of them can be defined in terms of Q gamma using this relation. So it's this works both for Q positive and for Q negative. This formula. And the generalized basic hypergeometric function is a kind of similar thing as the standard hypergeometric function, except for this factor. The meaning of this factor is to make good confluence relations. If we divide z by one of the parameters and let parameter go to infinity, we get a similar expression for lower order hypergeometric. This is why this. Anyway, if in the most important case when t equals s plus 1, this term becomes, this power becomes 0, and this term does not appear. Okay, here is our theorem. Again, we have to assume that the numbers are different modular integers. And otherwise, the formula is a kind of similar to the one we have in the classical case, except for instead of power of 1 minus z, we get this Q-Polynomial here with certain coefficient w. W is this expression here. And all I have said about the numbers beta also is true here. So we don't have an explicit, we don't have an explicit formula, but it can be done probably. Sorry, this is the conclude. Sorry, this was my theorem. Yes. Okay. What about the confluent case? Confluent, I mean when R is less or equal to R minus 1. I mean this index S here is less or equal the index here. Here something happens. Here we have to unfortunately use two types of basic hypergeometric function. This is the basic hypergeometric function I have just defined above. And this with the hat is the function of a similar flavor, but without this special factor. Unfortunately, you get a mixture. We couldn't derive a formula without a mixture for the same, for the product of phi times phi. Naturally appears this phi hat. Otherwise, the formula is a kind of similar formula, but the difference is that we have a product of standard basic hypergeometric, and this one, this time sometimes it's called Bailey's basic hypergeometric function, as Bailey used precisely this definition without this special factor here. Okay. Well, if I have some minutes, I give you an idea about the proof. I will only mention the proof of the classical case. First, we just multiply. We just use Cauchy product, so we get an expression like this. and then after certain simplifications, these numbers are these numbers. Then we split this into two parts. This is a kind of technical, but the most important step is to notice that this S1 is S1 is this expression is S1. The key point is to notice that this infinite sum can be seen as the sum of residues. Well, that's not precisely correct. Sorry, this part can be seen as the sum of residues. This is a finite sum of a certain rational function. And this rational function is here. It's not complicated. So if we define this rational function, then it's in a simple matter of simple calculation to see that this expression is the sum of residues over all poles of this function. And the condition that we have, that the numbers a should be different modular integers, is precisely the condition that all poles of these functions are simple, of all of them, with k equal from minus m minimum until infinity. Okay, so if this is a sum of residues, then we use the simple fact that the sum of residues of a rational function at finite points equals its residue at infinity. So what is residue at infinity? It is a coefficient at power z to the power minus 1 over z of the asymptotic relation of this type. So we have all this expression equals to this coefficient, which of course is a function of k. For each function, you have a different coefficient. This is the first key observation. The second key observation is that this coefficient that I have just mentioned, now we consider all the sequence of functions. We do not consider one function, but we consider a sequence of functions fk, and then we can prove that this c minus 1 of k is the polynomial in k of degree p, or simply 0 if p equals minus 1. After we know that, we can substitute back to the sum c1. This is our expression. We have just seen this equals to c minus 1. C minus 1 is polynomial according to lemma 1. Then we explicitly write the coefficients of this polynomial as nu L. Then we get this expression in view of the fact that this sum gives me it gives me something like gives me an expression like z to the power divided by 1 minus z to certain power. This is also a simple observation, and then we get the result basically. Okay, I don't have much time left, 1 minute, so let me mention some future directions. As I said, the explicit formulas for the numbers beta g would be nice to find. Then logarithmic cases, when the poles of our functions are multiple poles, then we don't have an explicit formula. This would be also nice to find. Then there is another class of kind of similar duality relations, but connecting f to 1 with f to 1 of 1 minus z. Because all of our formulas, the argument is always z, the same argument. There are Legendre identity, Elliott's identity, and more general Anderson, Vamanamurti, Vorinin identity. And I wonder if we can also generalize those and find the q-analogs. Then the original question I was interested in is to find a kind of similar reduction to combinations of Meyer G function. Here are references of what we have already published. Well, the last paper is just a preprint as of now. And these two papers are basically published. Thank you very much for attention.
Thank you, Professor Karp, for this interesting talk.
That's all.
I thank all the three speakers.
Sorry,
of
I
this
cannot hear
session.
anybody.
Is Professor Ahmad Ali around?
Yeah.
Yeah. I hand over the stage to you.
Thank you, Professor Sahai, for chairing this session. And I also thank all the speakers, Professor Tom Koornwinder, Professor Atul Dixit, and Professor Dimitrii Karp. Professor Dimitrii Karp, if you remember, you delivered a talk in the second meeting of SSFA, and this is the 19th meeting. So after 17 years, you have delivered another talk in this SSFA meeting. So I once again thank everyone for joining us in this session. Our next session will start at 5:30, which is the last session of day one of this conference. And this is a symposium on the works of Ramanujan. As you all know that this is National Mathematics Day being celebrated today in India. And the speakers in this symposium are Peter Pauling from John Kepler University, Australia, Aja Yi from Penn State University, United States, Frank Garvin from University of Florida, USA, and Kenon from University of Virginia, United States, and Rupam Burman from Indian Institute of Technology, Guwahati. So these are the speakers. I hope everyone will join us at 5:30. And I once again thank everyone, and see you in the next session at 5:30 Indian time. Thank you.
Thank you very much.
Thank you. Thank you.
Thank you.
Thank you everybody for attention. Yes.